Hello and welcome to the world of NDE 4.0. My name is Johannes Rahner. And today is a great day because today we'll finally continue our excursion into the world of ultrasonics. And today we will get to, in my eyes, a very important topic in regards to ultrasonic testing, actually in regards to all the testing methods which are around there. Can I detect what I am required to detect? And with ultrasonics, that's really, the question is ultrasonic sensitive enough to detect what I'm required to detect? So today, we'll be talking about UT detection sensitivity. Now, about a year ago, I did a video about ultrasonic sizing. And we talked about that for indications which are larger than the beam diameter. I can just use sizing by probe travel. So I put my probe here, I find that indication, then I move my probe, and then I see, okay, that's about the size of my indication. But that only works for large indication. What do we do with smaller indication? Now, indications which are smaller than the beam diameter, we can do sizing by the so-called distance amplitude size correlation. So we take the amplitude of our reflected signal and convert that amplitude in some information about our size. And there are different methods on the market. The two which are most likely the two most common ones is on the one side DAC, so using all those calibration blocks with flat bottom holes or side drilled holes drilled into them. And on the other side, the so-called DGS method, which is using those diagrams which are partially theoretically based and partially, experimentally based. And then you can take the diagram, for calibration, you can take it for indication sizing, and you can also take those diagrams to determine the sensitivity. And you can do something similar also with DAC, and I will come to that later in this video. But let's first look into what do we mean by sensitivity. And I guess within the next couple of minutes, you will see why I'm saying this is really the question: can you actually do what you're required to do? Can you reach the sensitivity you're required to reach? Can you detect all the indications you're required to detect? Now, if we look at, let's say, larger indications. Larger indications like this one, so we put our probe on our component and we will see an A scan, we will see our back wall, and we will see a signal coming up for that indication. So this is the back wall, this is the indication, and down here we have some noise. Now, we already said that with those distance amplitude size correlation methods, that our amplitude is correlated with the size of the indication. So if we would have a smaller indication, this means that the amplitude of the indication goes down, like this one here. And if we go to an even smaller indication, it goes down even further. And here I must already say, is it really possible to distinguish this indication from the noise? For me, I must say that's already a pretty hard decision whether we can see that indication or not. But if we go to an indication like this one, I don't see it anymore. If you can point it out to me, then I guess you're the better inspector than me. But no, I don't think anybody can see that indication. So it comes to the point that we need to define that from which point can we detect indications and under which level it's actually not really possible to detect indications. And normally what we do in ultrasonics, we take the noise level and we add 6 dB on top of the noise, and that's what we say that is our sensitivity. So this is this red line. Now, this is where we come to a balance. On the one side, we have our sensitivity, the sensitivity we can reach for this actual inspection situation. So the sensitivity will be different for every inspection situation we have. And on the other side, we have our requirements, our reporting requirements or our decision requirements. Now, if we look on the sensitivity, we said, okay, the sensitivity, yeah, that's kind of this red curve. And if we look at the reporting requirements, if I look into a procedure, a standard, or whatever, you normally find, yeah, you have to report indications above, let's say, a number 2 flat bottom hole or a 1 millimeter disc-shaped reflector. So you normally find a lower limit which you have to detect, which you have to report. And we can also plot that 1 millimeter or that number 2 flat bottom hole or whatever is required also into that graph. And that gives here this black curve. This is our reporting limit. And now we can compare those two. And easiest for visualization is we just overlay those two. And we can see that for a short sound path, that's no problem. We can detect what we are supposed to detect. But if we're coming to a longer sound path, it could be that starting from some point, we will not be able to detect what we are supposed to detect. Now, you might say, okay, but I can do an inspection from both sides of my component. Yeah, that might be correct. But then what you have to watch is exactly your middle. Because what you need a complete coverage of your volume ideally. But if you see something like that, if you see that you are required to detect an indication with a 1 millimeter, but your sensitivity is only about 1.1 or it's even 2 or 3 millimeters, then you should directly go to your level 3, or if you are level 3, you should go to your customer and tell them, I cannot inspect the part as I'm supposed to inspect it. And that could have multiple reasons, actually. It could be that the procedure is just not fitting for that component. It could be that that component just has a bad material composition, and way more factors. So for me, sensitivity is really one of the essential things we need to learn about our component, actually before we really get into a real inspection. And for me also, the sensitivity has to be reported in every single ultrasonic report. And I know a lot who do not report the sensitivity. They only report indications they found, but they don't report whether actually, yeah, the sensitivity was good enough so that they could really find those indications. Now, normally, the sensitivity is worst once we come to a long sound path. And therefore, for me, if we evaluate the sensitivity at the longest sound path we want to inspect, yeah, then that's the number which we can write down. And I will now show 3 different ways how to determine the sensitivity for a certain sound path. So not like here with a continuous curve, but just the information for, yeah, an overall information. And I'm doing that in the following: first for DGS, afterwards for DAC, and afterwards for TCG or TVG. So if you're just doing DGS or just doing DAC, just skip the parts you are not really that much into. So let's start with how do I determine sensitivity using DGS. Now with DGS, we already talked about DGS in a video I did about 3 months ago, and I will leave a link to that video right here. And in that video we said, okay, first thing is we need to put the probe on the component. We have to bring up the backwall to 80%. We adjust the gain so that the back wall reaches exactly 80%, we note down how much gain we needed to bring it up to 80%. We also measure the sound path to the back wall. And with that information, we go into the DGS diagram. We look on the back wall curve. That's that curve marked with that infinity sign. The curve which is all the way the most upwards curve. And we'll look for the sound path of 600 millimeters. And we can see that, yeah, it's this point we are interested in. And we'll look for the value we can read from that point. And we see that we have about 19 dB. So we get 19 dB from the diagram. We have 12 dB for our particular inspection. So we have a difference of about 7 dB between our inspection and the graph. So that's the conversion we also have to keep in mind and we have to write down for the future. Now, if we would want to size an indication with that, we would have, okay, bring the indication up to 80%, go back into that diagram and read that indication. If you want to know more about how to size an indication, go to the video about the DGS method. Here, I want to talk about now how to determine the sensitivity. So we have done the calibration using the 80% back wall. And now we want to determine the sensitivity. And now remember that we want to have a 6 dB difference between our noise and our sensitivity. So if we want to put sensitivity to 80%, then we need to put the noise to 40%. And that's exactly what we're doing. We're pulling up the gain so that we reach the 40% screen height. Yeah, and then we go back into the diagram. Again, we have a certain gain it needs to bring the noise actually up to those 40%. And then, yeah, we add again those 7 dB and we get into the diagram and we can directly read that the sensitivity is 1.1 millimeter DSR. Meaning, if we have a requirement of that we have to report indications starting with 1 millimeter, that means that, yeah, in a reliable way, we cannot detect all the indications we want to. If the indication would, if the sensitivity would be 0.9, then we could say, yes, we can detect everything our customer wants us to detect. And if the sensitivity is up to 2 millimeters, then, yeah, no way that you can detect a 1 millimeter. I guess you see where I'm going to. Okay, next method, DAC. Now we're using calibration blocks for our calibration. And first step is, yeah, we take those calibration curves and we create our DAC curve, which is shown here in our diagram. And this could be, let's say, for a number 2 flat bottom hole, for a number 4 flat bottom hole, for whatever flat bottom hole you want to use. Next step, you measure your noise level. And you would think at this graph here, at the end of our sound path, so meaning at 600 millimeters, we have about 12% noise level. And usually if we would need to size an indication, we would use the inverse square law, which I guess most of you will know. But remember again, our noise level and our sensitivity will want to have a difference of 6 dB. For that difference, we have to introduce a factor of 2 to determine the sensitivity. Now let's do that. Now let's say we have as a reference reflector a 1 millimeter flat bottom hole. We have our DAC curve at the end of the sound path, it's 20%. And if you do the calculation, then we come up with a sensitivity of 1.1 millimeter flat bottom hole. So again, the same like I said before with DGS. Sensitivity of 1.1 means that you will not be able accurately to detect a 1 millimeter. Yes, in some cases you might be able to find a 1 millimeter, but it's the reliability we're speaking about. And that's the big issue we are facing here. So always measure your sensitivity. Measure your sensitivity before you really get into the inspection. And if you find that your sensitivity is not good enough, inform your level 3. And best inform them in a written form so that they cannot say they haven't seen it. And if you are level 3, inform your customer also in a written form so that your customer cannot say, oh, but you didn't tell me. Because this comes down to actually in a reliable way, you cannot detect those indications on a long sound path. And perhaps that might be a risk for your customer's components. And your customer really has to take the responsibility for this and not you as an inspector. Third method, TCG. I haven't done a video about TCG up to the moment. Perhaps I will do one in the future. TCG is time-corrected gain, or sometimes you also find time variable gain. The meaning is, what you do is you apply a different gain depending on your sound path. On a very short sound path, you anyway have a very strong signal from a potential indication. And therefore, you don't need that much gain as you normally apply. So you only apply a couple of dB. And the longer your sound path gets, the more dB you apply, the more gain you apply. And what that leads to is that this curve we saw before with DGS, or also with DAC, that this one becomes a straight line. So now our decision requirement is not anymore a curve, but it's a flat line. On the other hand, our noise is not anymore kind of constant. Our noise is getting more and more amplified the longer the sound path, and therefore our noise level is also going up. Now, you can create such TCGs using DGS. You can create such TCGs using DAC. You can create your TCGs with whatever methods you want to use. Again, we use the same formula to come up with the sensitivity level. We use the modified inverse square law with that factor of 2. And if we do that, in this case, let's say we have a reference reflector of 1 mm flat bottom hole. We have a noise of about 24%, and let's say and our reference level is at 40%. We calculate that and we see our sensitivity is 1.1 mm flat bottom hole. So again, we will not really be able to detect those indications. Okay, now I guess you will see why I think sensitivity is such an important factor. However, there might be a small issue. And that's the determination of the noise level, the measurement of the noise level. Here, this is nice artificial data, and we came up with a number for the noise. But already here, I guess a couple of people would say, oh no, that's not 24, that's perhaps 20% or 12% or whatever. So to get a better grasp how other ultrasonic experts are dealing with the challenge of determining the noise level, I did a survey, and I did the survey 2 times. I did that survey at a former employer of mine, which is kind of an enclosed group, so you would think that they would kind of give more similar results. And I also did it on social media, where we had people from all different groups of inspectors. And what I did, I showed them actually data from an automated scan. And that automated scan had 40,000 points, or 40,000 A scans. And I always took the last bit before we came to the back wall. And that is what is showing here. So this is one time going around the component. Those are 40,000 points, always the longest sound path. That's what I'm showing here. And you can see somehow the average of this noisy structure is at 0.43. And if we calculate the standard deviation, that's about 0.12. You might say it's better to take the root mean square. Yeah, I also calculated the root mean square, that's 0.45. But what do experienced level 2 and level 3 inspectors say that this noise level is? Yeah, nobody said 0.45. The lowest answer I got was 0.5. The highest answer I got was 1. And about everything in between. So that's a factor of 2. And this is actually the scale here is in millimeter flat bottom hole. So between 0.5 and 1, that's 12 dB and 12 dB difference between the lowest and the highest in the determination of the noise level. And if people already have 12 dB in determining the noise level and difference, then yeah, how to really accurately determine the sensitivity. Now, still, I think it's really important that, yeah, that you do an accurate job in determining the sensitivity, that you put out a value for the sensitivity, and that you kind of, within your company, that you come, or with your customer, you come up with a certain way how to determine its noise level. So it's always the same values which get reported, so that your customer knows how good or bad those components are, how good or bad the material quality is. Because sensitivity tells a lot about the material quality. And if we look here on this graph, we kind of see that if I look onto the different answers, we get kind of a bias to about 0.8. And 0.8, yeah, there are some noise peaks coming above that, but it's only a couple of them. As I said, it's about 40,000 A scans. And in about, I would think it's about 10 of them, we get a signal above the 0.8. So I think that this could actually be a good number for the determination of the noise level. And in a video I will do in a couple of weeks, we actually came up with an automated way how to determine the noise level, and then how to actually determine the sensitivity for an automated inspection. But that's a topic for a future video. Now, I hope that this video was as interesting for you as it was interesting for me to prepare this video and to get into the topic of sensitivity. Next time, if we're talking about ultrasonics, we will get to a topic I already promised you a couple of weeks ago, and I think you will get very excited about it, because we will be getting into reconstruction technologies. Now, we will not be talking in the beginning about TFM, because TFM, I think before we get into TFM, we have to do something simpler first, and that's SAFT, Synthetic Aperture Focusing Technique. And that will be, I guess, somewhere in October that I will publish the video about SAFT. As usual, you will find more information about the sensitivity topic in the description. I hope you like this video. I hope you subscribe to this channel. I hope you give me a thumbs up. I hope I will see you soon. So thank you for watching. See you soon. Thank you and bye.